Good, good.
All right. So then let me go ahead and introduce you. We'll be here all day, Jim. You know everybody here. So
I know a few people, but yeah.
all right. So let me introduce our speaker. So it's a pleasure to introduce our physics club speaker for today, Professor Jim Napolitano. I wanted to say that I actually have known Jim before he knew me. We were both graduate students at Stanford. Jim got his PhD at Stanford in 1982. And we overlapped maybe for a year or so. And here was this guy that, you know, he was the big star and I was just the new kid on the block. But since
Keith is being far too generous with his money.
Well, I don't know. So Jim has a wonderful record of experiments, successful experiments that he can brag about. He was part of the Diabet measurements that happened shortly after, I think, Karsten came here to Yale. He also is part of the Prospect experiment at Oak Ridge National Lab, working with a number of people here. He's worked on the CLEO experiment. He's also done experiments at BNL, the multi-particle spectrometer there. And you did work at Argonne Lab as well. As I recall, you came to Jefferson Lab right after finishing your work at Argonne Lab. So I met Jim where he actually knew me and I knew him at Jefferson Lab. I think he was there for a couple of years before I came. And the one story I want to tell, I always enjoy telling this story. I was proposing an experiment there after a few years of work there. I was going to propose an experiment and the experiment was headed for oblivion. And Jim Napolitano saw that. He pulled me to the side and he coached me and told me how to make presentations, what I need to get up to speed on, and the experiment got approved. And this was a Kaon experiment, and that led to other success. And so I always say that I owe my gratitude to Jim for coaching me and preparing me for this, and including getting noticed at Yale. So Jim is now going to talk to us about precision electroweak measurements. And I also wanted to say that Jim is part of this precision molar experiment at Jefferson Lab. And when he told me how much funding it's getting, it almost is a small national lab by itself. But anyway, it's a pleasure for me to introduce you, Jim. And so take it away.
Well, thank you, Keith. I think I have to have you come down and give a seminar or colloquium here so that I can make it clear about all the things that I did and didn't do to help your career. Just everybody should clear. Keith was the star. He did some amazing stuff, and we were all really pleased to work together back in those early days when our kids were little.
I know. We had officers.
We were just comparing ages of our daughters, and they're the same age. And
it's amazing. Yeah.
Okay, good, great. Thank you very much. I mentioned to Keith and Bonnie earlier that I came close to deciding, instead of taking the train to my office this morning, to instead take it to 30th Street Station so I could hop a train up to New Haven, because I would have loved to see people in person. But some other time it would be great to come up and see people. I'm going to share my screen in a second, but let me just say at the outset, I really would like people to ask questions. I'll do my best to try and identify people who raise hands and stuff like that, but feel free to just turn on your mic and ask a question if it comes up. And I think these things always go well when we can have more interaction. So let's see how it works. Please ask questions, especially students, Okay, so let's turn things on. Okay, so everybody can see my screen, I guess. Somebody say yes.
Yes.
Yeah, okay,
yes.
Good.
Yeah.
Okay, good. And I've got my cursor here, which I guess you can see as well, right, Keith? That worked before. It probably works now. So what I want to tell you about today are some two experiments in particular that have to do with precision electroweak electron scattering at GeV energies. And a subtitle would just be parity violating electron scattering, because that's the tool that we're going to be using to make these two different measurements I'm going to be talking about. I suppose most of you know Jefferson Lab is this laboratory in Virginia, which has an electron accelerator of, it produces really outstanding quality electron beams. And that'll be critical for the stuff that we're going to be talking about. Oh, great. Now, how do I advance? Oh, I guess that's how. You know, whenever I give a colloquial on this kind of stuff, I always like to start out by talking to people and telling them about how confused Newton would be by what this idea of an elementary particle is. I heard a presentation a long time ago, I think it was by Violating, who pointed out that if we were the size of femtometers, the world would look tremendously different to us. The biggest difference is that at that distance scale, energy and matter exchange their roles. It marries quantum mechanics and special relativity. So the whole idea of what matter is, what energy is, these things all become very confusing when we're at distances of femtometers or smaller. So when we draw things like these diagrams that show us all the different generations of matter and how, you know, what the interactions look like, what we're really doing is just listing all of the quantum mechanical states that we can have and how they fit into field theories. So we're doing physics at a regime where the energies are so high and the distance is so small that even though we use words like particle, which might be familiar, we always have to remember that we're really studying interactions and things at a very profound level where matter and energy are interchanged constantly. So this is something you want to keep in mind when we talk about nuclear physics, particle physics at these really small distances. And for today, the players that are going to be important are the up and down quarks, the electrons, and an interplay between the photon and the weak neutral Z0 boson. All the stuff that I'm going to be talking about today is making use of these both as tools, things that are perfectly well understood in the standard model, but we can use them to study some other systems and to test the standard model itself. So that's really what we're going to be doing. Two different experiments are the things that I'll be talking about. One has to do with neutron stars, and I'll tell you how we can use parity violet electron scattering to study neutron stars, and I'll tell you about some results that just came out this past year, and one, in fact, that just came out a few weeks ago. And the second is the next experiment we're going to do, the so-called Muller experiment at Jefferson Lab that Keith alluded to, which is going to be searching for physics beyond the standard model. And that's the experiment we're doing next and working on now. So for those of you out there, especially students who get a little bored and confused with one topic, hang on, because very soon we'll switch to a different physics topic in a different experiment. But the first thing I want to do before we talk about either of them is talk about this tool that we're making use of, namely electron scattering. So an electron with an incident electron has a form momentum k, scattered electron k prime. The electron comes in and scatters off of some target. When it does that, it exchanges something. You all know this. We'll talk about the exchange particle in this case being either a photon or the Z0 weak neutral boson. We're doing this at pretty high energy, so the momentum transfer, the difference between the form momentum of the scattered and incident electron, is pretty big. So the distances are small. We are definitely in this regime where Fermi femtometer type scales, where matter and energy are exchanging roles all the time. The critical thing about these experiments is that we're going to make use of the electron spin. And we'll always be quantizing it for the purposes of this talk in the direction of the incident electron or opposite the incident electron. So electron spin can be right-handed or left-handed. And this is going to be the critical component that we make use of in parity violation. The difference between the two experiments I'll talk about just have to do with what target we're using, and also things like the specific energy and scattering angles and whatnot. But in the case of neutron stars, we're going to be talking about scattering from two nuclei, lead-208 and calcium-48, which are both so-called doubly magic nuclei. They're very spherical. And they both have excess neutrons. In fact, lead-208 and calcium-48 are the only two neutron-rich nuclei that are doubly magic and that are stable enough so that you can do an experiment with them. The second experiment, the target is simply going to be another electron. So that'll be electron-electron elastic scattering, a process which is perfectly predictable in the context of the standard model. So those are the two experiments we'll do. We'll all going to be doing this with electron scattering. The key here is that we'll be using parity violating electron scattering. Now, you'll all likely remember that if you take something that has a spin, like an electron, and you look at the same scattering process in a mirror, the momenta don't change. They all just go in the same direction, but the spin reverses. So if those two processes that are drawn here, the one in the real world and the one in the mirror, if those two processes are not the same, then that's called parity violation. It's now pretty well understood. And in fact, the details of how this works are completely specified to arbitrary precision by the standard model. So we're going to be making use of this in the stuff that we're going to talk about today. The thing that you have to realize that really makes these experiments challenging, though, is that the effect is very small. In this case, the parity violation comes from an interference with the axial vector components of the Z0 exchange with the photon exchange, which is purely vector. So if I draw, this is just a schematic where you see what the cross-section would look like for the spin in one direction compared to the other. The thing that changes sign is the Z0 part. And if I draw these amplitudes as, so that the cross-section is the square of an amplitude, and the amplitude is the sum or difference of the exchange of the photon in the Z0. The photon in a Feynman diagram, I just draw the propagator as a 1 over q squared. In the Z0, the propagator has the mass of the Z included. And the momentum transfer, q squared, is much, much smaller than the Z mass squared. So we ignore the q squared in this denominator. This really doesn't play any role at all. And the asymmetry, which is the difference in the cross-section divided by the sum, is sensitive to that interference, which basically works out to be q squared divided by mz squared. That is a very small number for the q squareds that we'll be talking about these experiments. We refer to them in parts per billion, ppb. So we're measuring scattering asymmetries that are several parts per billion, sometimes several thousand parts per billion. So I should say parts per million, but I'll keep ppb as my unit of choice here. And the details, of course, of the scattering depend on how the interaction behaves with the target. That's how things work. And I'll show you what those differences are. I want to remind you all to ask questions. I realize now I'm doing this in full screen, so I can't see you. So please just shout it out if you have questions. If I was there, I'd look people in the eye and ask them, but I'm not. Okay. Remember, the standard model tells you exactly what all of these different couplings are, and we can use this to do a lot of physics. It's the axial vector couplings of the Z0 that gives you the parity violation. So knowing what those different Z0 axial couplings are is key to figuring out what's going to go on. And you get these different combinations for the electron up and down quarks and the proton and neutron when you put things together. One thing that makes it possible to do a lot of this is that the weak mixing angle, sine squared of the weak mixing angle, is very close to a quarter. So you have a 1 minus 4 sine squared theta w for both the electron and the proton. Those couplings are small. And that makes a lot of what we're talking about possible. I'll get into some of those details, especially between the proton and neutron. The fact that the proton is very small compared to the neutron axial coupling is how we're going to learn about neutron matter in lead and calcium. Okay, here's a little bit of history. The first electron scattering parity violation experiment that was successful was at SLAC in 1978. This was a real big deal. I imagine Keith remembers this too. I was a brand new graduate student when this experiment was released. And we all heard about how difficult it was to build a polarized source. But once they had all that, make the polarized electrons, they actually confirmed the standard model. And I remember when this came out, everyone said, well, the right answer is SU2 cross U1. It was a real big deal. A number of other experiments have been done over the years with the parity violating asymmetry that I've listed here in parts per billion. So you can see a number of them are actually a few parts per million. And this is the uncertainty. And you can see that as time went on, these experiments got more and more precise. That means you're not only sensitive to tiny, tiny effects. For example, in Q weak, they were sensitive to uncertainties of 9 parts per billion, which is also a very small fraction in precision-wise of the actual asymmetry. So this has been the real trend to try and do more and more precision, and we'll talk about that. The history is long and checkered. Yale actually had a very important role in the second one on this list, the carbon-12 elastic scattering parity violation. This was conceived and eventually pulled off by Vernon Hughes, Paul Sauter, and their students at the MIT Bates Accelerator in Massachusetts. I'd also want to point out that 2 of these experiments are very similar to the ones I'll be talking about today. In 2005 at SLAC, E158 did a test of the standard model by measuring a relatively small 117 parts per billion asymmetry to plus or minus 16 parts per million, so not quite 10%, 10% level of precision. PREX-1 was the first attempt to measure the so-called neutron skin thickness with relevance for neutron stars. It was only a 10% measurement, and even though that's quite a tour de force, I'll show you soon that you need to do much better than that to have a real impact on neutron stars. That experiment was faltered a bit because it just turned out to be really hard. You pour a lot of electron beam on a lead target, and it puts neutrons all through the experimental hall, and some things died much more quickly than people were prepared for. So anyway, that's what we're going to talk about, and that's where we're going with this. Let me just show you a little bit how this stuff works, because one of the things that people make a point of all the time talking about these experiments is that it's not just an electron scattering off of the target with some detector. The whole accelerator, including the injector, is part of the experiment. I got a kick out of this. The young people out there might not know the term microcomputer. Today we just call it a computer. But the real important point to recognize here is that the polarized source, which for this experiment used a gallium arsenide photocathode, goes through the accelerator, and all these different monitors would measure the current, the energy, the position, the angle, all of these factors that could be different for one polarization direction for the other. And they all have to be fed back to try and measure these tiny asymmetries so that you get something that's consistent. In this experiment, they scattered off a liquid deuterium, built a spectrometer, and just measured the whole wad of electrons that scattered into the spectrometer. They measured the beam polarization with a molar polarimeter. And it really worked out well. One of the nice things that they had was that you can go in and by hand flip the polarization of the beam by moving a prism between 0 and 90 degrees. Everybody follows this rule now, something that everything in the accelerator does not know about, but tells you that you should change the sign of your asymmetry. And sure enough, they saw things correctly switch between the prism in one direction or the other. They were able to measure this asymmetry and show that it was what you expected by the standard model prediction for electron couplings to quarks. So that was a really big deal. And the standard model was verified, and it's been tested obviously very much since then, and we always seem to get the right answer. These days, we do these experiments at Jefferson Lab, where the beam is very precise with a lot of control, an outstanding polarized source, which now uses a strained gallium arsenide photocathode. It's a little technical, but the point there is that you could get above 50% polarization. Right now, we routinely get polarization of the electron beam approaching 90%. I'll show you some of those results a little bit later. Oh yeah, it's kind of cute. They have a little picture, a little statue of Thomas Jefferson that is constantly blessing the polarized source. And for those of you who know how things work at Jefferson Lab, all the experiments I'll be talking about today, the 2 experiments, are all done in Hall A, which is the large hall, which is beam right as the beam exits the accelerator. I'll show you some pictures of that on the inside. Okay, I really want to stop for a second here and invite students, anyone, to ask questions. Once again, I can't see you, so just shout it out if there's something people would like to say. Otherwise, I will just go on. Okay, so here's the first of the two physics topics that I want to talk with you about today. We'll use parity violation to learn about neutron stars. The history of neutron stars is absolutely fascinating. There's still an awful lot we don't know, because neutron matter is something we haven't been able to study. But one of the things that we can study are neutron-rich nuclei. And this can tell us a little bit about neutron matter, and that'll help us learn about neutron stars. And that's the entire point. Neutron stars are not only fascinating from a historical perspective, there are some amazing things that have been happening relatively recently. One is that we can now see neutron star mergers in gravitational waves, gamma rays, and also optically. This is a picture of the gravitational wave event 170817. And if you look at those two papers, you can see about the gravitational wave experiment. You can also see the result from the Fermi Gamma Ray Observatory and how they were able to observe it optically. These are optical images of a distant galaxy. And right here, you see the gamma ray burster that was able to pinpoint. Seeing these things about gravitational waves, optical and gamma rays can tell you about the materials and how things are actually being constructed when two neutron stars merge and they deform. Tidal variations of neutron star mergers, how much energy is given off in different wavelengths. It's very cool to note that it looks like neutron star mergers are where the S process elements are made, the very heavy elements that seem to have been made with rapid neutron capture. But we don't know enough about neutron stars. The experiments I'm talking about will help you try and figure out how stretchy they are and how they get deformed in a merger. There's also these nice results. I've got a couple of them here, two different measurements of some particularly massive neutron stars. Neutron stars have now been clearly observed whose masses are greater than two solar masses. Two solar masses. That's surprising because the Chandrasekhar limit for white dwarf stars is about 1.6. So somehow neutron stars need to be more stiff. Neutron matter is stiffer somehow than electron matter. And we don't really know how that happens, because most of the ideas people have come up with for neutron matter makes the equation of state softer, not harder, so not stiffer. So we've got a lot to learn. And if we could figure out ways to study neutron matter, that would be wonderful. So what we can study are so-called neutron skins using parity violating electron scattering. And this is a very recent paper that actually interprets our result from PREX. It's a good place to start if you want to learn more about this. But let me walk you through it. What you'd really like to study is a nice spherical ball of neutrons, but that doesn't exist. We can't do that. You can, however, study a spherical neutron-rich nucleus like lead-208 or calcium-48. So this is my model of a nucleus here. If you look up in any classic nuclear physics textbook, you'll learn about the liquid drop model. And it'll tell you how we get the energy, the binding energy of a nucleus, by considering the different components as if it had hydrodynamic properties. What I've shown here, subtracting off the mass of the nucleus, is the residual binding energy. And there's some energy of symmetric nuclear matter, where neutrons and protons are the same. But then there's a term having to do with the symmetry energy. And this depends on the difference in densities of neutrons and protons. What we'd like to know is what this quantity is when the proton density is 0 and all the density is neutrons. We can do that by studying the symmetry energy for different neutron-rich nuclei. We usually write the symmetry, as the people that I've been studying this from, write the symmetry energy as a function of pressure as some constant, which I don't really care about so much, times something that we call L, which is the symmetry pressure. It's effectively the symmetry pressure having to do with the neutron matter in particular. And as I'll show you in a moment, what we can measure directly is the skin of this nucleus. This is the neutron skin of a particular nucleus. And this is a graph from Reed et al. That show you what the correlation is between the skin thickness and Fermi's. We want to measure this as precisely as we can. And that infers what the pressure is, the pressure term L. The plot here is for a bunch of different calculations to show you that there is a very strong correlation. Correlation is particularly strong when the density is 2/3 of saturation density inside of the nucleus, which is closer to where it is on the outside, which is where the skin is, obviously. So there's a very strong correlation between the skin thickness and the symmetry pressure, L, and L is what you need for calculations of neutron matter and neutron stars. So we're going to measure R and interpret that in terms of L, and then see what it has to do with neutron stars. How do we measure the skin thickness? Well, the first lesson is that we do it with electron scattering, elastic electron scattering. And you all likely remember from your quantum mechanics course that the scattering is affected by a form factor. The amplitude multiplies a form factor, which is essentially the Fourier transform of the density of whatever it is you're scattering off of. Also, you know, in those courses, you expand this for small q, for small momentum transfer, and you get 1 minus this term. And this, of course, is just the the mean square radius of the charge distribution. And that's how people for a long time have measured the radius of the proton, radius of nuclei. And I'm not going to go into that in any detail, but that's where it comes from. But here's the reason it's so important. That term tells you the mean square radius of whatever it is that your probe is bouncing off of. In our case, we have two probes, the photon and the Z0. And remember, the photon couples to charge, so that's sensitive to the proton. It's really insensitive, essentially insensitive to the neutron. The Z0, on the other hand, doesn't couple to the proton so much. It mostly couples to the neutron because of that 1 minus 4 sine square theta factor. So now if I form my parity violating asymmetry, I get my q squared over mz squared term, which is essentially this. The Fermi factor mostly has that built into it along with alpha. The important thing to realize is that that ratio now has the ratio of the z form factor as a function of q to the photon form factor as a function of q. And if I do that same expansion for these two, where q squared is small, then I get 1 minus q squared over 6 times the neutron radius squared, mean neutron square radius, minus, because it's in the denominator, the proton radius. So now you see how we get the neutron skin. The parity violating asymmetry is more or less directly related to the difference in the mean square radii of the neutron and proton distributions in the nucleus. So that's what parity violation gets you. But this is where the rub comes in. This is a small term. This q squared is designed to be small enough so that I can do this expansion. So this second term here is small compared to 1. So I've got to make a very precise measurement of this parity violating asymmetry so that I can extract a reasonable and useful measurement of the difference in the squares of the neutron and proton distributions. That's why these experiments are particularly tough. Here are just a few numbers to put in. I'll highlight some things in a minute. But lead's a large nucleus, and we use that to really study nuclear matter. Calcium-48 is a much smaller nucleus, but microscopic calculations are tractable. And this is what we're trying to do with the neutron skin of calcium-48. I want to point out to you that the precision we're looking for is about 3% in P-Rex. That old experiment got about 9%. And the difficulty of the experiment goes like the square of the precision. So P-Rex2 is 10 times harder than P-Rex1 in that sense. Calcium-48 we call C-Rex, that's 2.4%. So we're trying to make just a few percent measurements of these really small numbers, and that'll hopefully get us some precision in the skin thickness. I also want to point out that in these nuclei, they have excited states. We don't want to scatter from those excited states. We only want to know the elastic scattering, and we're doing this with 1 or 2 GeV electron beams So we have to do this with pretty good resolution to make sure we're only looking at elastic scattering. For that, we make use of these nice spectrometers in the hallway at Jefferson Lab. I'll draw the electron beam there for you so you can see where that goes. The target that you want to scatter from is somewhere in here. And there are these two identical spectrometers called the high resolution spectrometer left and right. For our experiments, they were placed symmetrically very close to the beam, actually with a septum magnet, for those of you who are experts in this, to get very small angles for the scattering. They're not symmetric in this picture, but I just want to show you the scale. They didn't put any people in this picture, but you can see the personnel ladders. You get some idea of how big these things are. Actually quite large instruments. I want to put in some of the numbers for you for lead so you can see the scale of things. So that's our formula for the parity violating asymmetry. And I'm going to do is take the difference in the squares of these and write them as the sum and difference of the square roots. And the sum, since the skin is not particularly thick, is pretty much just twice the radius of lead. And this really is the skin thickness, the difference in the RMS distributions for the neutrons minus that for the protons. You put in some of the numbers. This is the momentum transfer we ran at, what the radius is for lead. A 3% measurement of this small parity violating asymmetry gives us a 0.07 Fermi skin thickness. The skin thickness is about 0.2 Fermis. So all in all, if we really beat ourselves up to measure this parity violating asymmetry to 3%, we're going to get about a 30% measurement in the skin thickness. Again, that's because this term is small compared to 1. So we really have to do a good job measuring the parity violating asymmetry. And we did. The result was published this past year. There's the reference. This is the badge of honor for parity violation experiments. How nice and Gaussian, perfectly distributed is your series of asymmetries. This is 3 million asymmetries from sequences at 240 hertz, taken every 1/30th of a second. And after a lot of work correcting for all the beam motion and all the beam current and charge, a number of different corrections, we get a parity violating asymmetry measurement that's in fact quite good, about 3%. This is what you get for the form factor. And if you correlate the parity violating asymmetry that we measured with the, in this case, the weak radius, which you can then turn into a neutron skin radius, you can see our neutron skin ranges in here. This correlation is based on a number of different calculations where you can vary some parameters. I've been giving you a very simplified view of what the relationship is between the parity violating asymmetry and the skin thickness. There are a number of corrections you have to include, but the correlation is still obviously very strong. So after all that work, we indeed get about a 25% measurement of the neutron skin thickness of 0.283 plus or minus 0.071 Fermis. Great, it's nice to have that number, but this actually made quite a splash. I suggest you take a look, if you'd like, at a Physics Today article, which they called "Lead-208 Nuclei Have Thick Skins." And Kate Schulberg, if you know her, wrote this really nice article for Physics that advertised our results. It's got a lot of good descriptions in there, as well as some nice references if you want to learn. Physics Today published this particular view here of the distribution. We measured this difference in here between the skin thicknesses, but here's the reason people care very much over here. These are a number of calculations of what that symmetry pressure L is in different types of nuclear matter calculations. Our result is here. So we disagree with those quite a bit. And that's it's a statistical error almost entirely. Our systematic errors were very small. But nevertheless, we don't seem to agree, hence the idea that we have thick skins. The pressure is larger than what people expected it to be. CRAX with calcium-48, we just released that result. This is what our parity violating asymmetry is. a 4.3% error, again, mostly statistical. I don't have a value for the skin for calcium-48 yet because there are some nasty effects that have to be sorted out. We sort of got caught with our pants down, to be honest. This is a paper by Chuck Horowitz and Jorge Pierowitz from about 10 years ago, and it points out that there's a weak spin orbit effect that has to do with the way the shells in calcium-48 are arranged. And we need to understand what that is before we can come up with the skin thickness. But this result here on the left plots the difference in the charge and weak form factors for calcium-48 and lead-208. And what you can see pretty clearly is that our lip for these two sits around here. We're not on this line. This line is drawn through a bunch of relativistic and non-relativistic density functional theory calculations. So some work's going to have to be done to understand how to modify those results in order to understand neutron matter as well as lead and calcium. But that's the reason we did the experiment, to try and see how much we knew. And it looks like we don't know as much as we do. So there'll be some more work to try and understand the best way to do these nuclear matter calculations. And I would recommend you invite Chuck or Jorge or some of their collaborators if you'd like to hear about the theory end of this argument.
Jim,
Yes.
Quick question. Have you or any of the theorists considered other possibilities, like this difference between the measurement and the theory, including new physics, new phenomena?
And the short answer is that's what's going on right now, particularly because the result we got from calcium-48. I mean, if the calcium-48 result was up here, everybody would have been happy. And that was sort of what we were expecting after we got the lead result. Now that we have these differences, people are looking in lots of different places to understand what the results are. So yeah, you can take a look. One of the things that really struck us was that the P-Rex result has a lot of citations. As soon as we get the C-Rex result published, which will hopefully be in a couple months, I think you'll see a lot of people considering lots of different ways to interpret this stuff.
Great, thanks.
Sure. All right, great. So much. Oh, yes, I wanted to point this out. Sorry. It'll become more important later, and this is also where my group spent a lot of their time working on measuring the electron beam polarization. I don't want to spend a lot of time on this. We measured the beam polarization to about plus or minus 0.5% precision, which we believe is the best anyone's been able to do. Well, we know that it is, and at these energies, and this will be necessary for the next experiment that we talk about. It's very cool. If I come up to Yale for a technical talk, I'd spend more time talking about how we made these measurements and where we're going with it. But we're pretty proud of this. We're able to do so well. Okay. Second physics topic that I'll conclude on, how do we use parity violation to test the standard model? Well, what we're going to try and do is measure the weak mixing angle using electron-electron elastic scattering. And this plot gives you an idea of how things are. Notice how expanded this, how suppressed the zero is for this plot. These are all very precise measurements of the weak mixing angle. One of the things that's particularly interesting is that there seems to be a bit of a discrepancy here between the LEP and SLC measurements, both with each other, although they all seem to fall pretty much on the line of the prediction. Essentially, what we want to do is see if this is affected by new bosons, new intermediate force particles that exist at particularly high masses. This is an example of what we would call doing high energy physics at low energies. And this is a way of explaining that I stole from Howard Georgi when he gave a talk at Jefferson Lab probably 30 years ago. So I've drawn here a potential energy curve. That's a simple harmonic oscillator, right? Everybody recognizes it. Simple harmonic oscillator potential. And if you take this thing and you look at oscillations between plus and minus 1, you get a nice curve that certainly looks like a sine curve. So everything looks wonderful. But suppose you measure that motion more precisely. What I've done here is subtracted what this curve is from a real simple harmonic oscillator. And you see at the 0.1% level, there are deviations. It's not simple harmonic motion. I did a very precise measurement, if you will, of a well-known process. And what I discover is that there's a discrepancy. Well, why is there a discrepancy? It's because this is not a simple harmonic oscillator. If I expand the scale by many orders of magnitude, what I realize is that I'm just looking at the bottom of some curve. That's not a parabola. So the lesson here is that you can probe very high energies by making very precise measurements at low energies. And that's what we're doing here. We're going to make a measurement at energies on the order of GeV, momentum transfer Q squared, that are fractions of Jev squared. And we're going to use this to probe physics at the 10 TeV scale. We do that because the calculation of Muller scattering, and it's a play on words, right? The experiment is called a measurement of lepton elastic reaction, which spells out Muller, which is the name of the scattering process. This is perfectly calculable, and we're going to look for deviations from this calculated result. The symmetry is 33 parts per billion, and we're going for a precision goal that's only 2.4%, everything put together, 0.7 parts per billion sensitivity. And to estimate your sensitivity to new physics, you can put in a new energy scale. We call it lambda, and this is where our experiment will be. These are the other experiments that have measured quantities that are sensitive to the weak mixing angle. By measuring things at this level of precision, if we don't agree with the standard model, then we're sensitive to mass scales that are about 100 times the current Higgs scale, maybe 50, 75 times larger, about 7 to 10 TeV. So that's the idea. Measure something where the result is perfectly well known, and let's see if it agrees. If it doesn't agree, we're probing energies that are much higher than anything that we can reach directly. So we do this with elastic electron-electron scattering. The electron beam comes in here, scatters off the liquid hydrogen target, and then the two electrons, which are very, very close together in angle, get split apart by one toroid and then another weird-looking toroid and detected down here in different detectors. It's about 30 meters from front to back. This really is a weird beast. This toroid, engineering it has been a bit of a tour de force, but it bends the electrons out and separates the electrons that scatter elastically from electrons in the target from ones that scatter from protons in the target. And this shows you what the distribution looks like in radius when you get back to the detectors. So between 0.7 and 1.3 meters, that's the radii up here where the detectors are. The gray band here is where all of the Muller scattering, electron-electron elastic scatterings occur. The pink here is the elastic electron-proton, and the magnetic system separates those effectively. One of the really cool things about this is that the toroids have a 7-segment structure. There are 7 segments, which means that the electrons, the 2 electrons that are in the scattering process, one of them will be accepted and the other gets blocked out by a collimator. But since there are 2 electrons in each scattering process, we essentially detect every Muller scattering event. We need that for the statistics in order to be able to get the sensitivity that we need statistically. So the detectors at the lower radii detect the elastic electron protons. The one in the so-called 5th ring are the ones that will detect the Muller scattering electrons. The detectors look like this. It's a series of Cherenkov detectors that just detect the light from either the Muller scattering electrons or from the elastic electron protons, and the different detectors at different radii. So we have all of these assemblies set up all around the ring in the sensitive regions where the scattering happens. This is part of the reason this is an expensive experiment. It's got lots of different pieces that we need to make sure we can control all the systematics that are involved. For those of you who like technical details, these are some of the ideas where the scattering rate is enormous, 123 gigahertz. That's the Muller scattering rate. We do not even come close to trying to count individual particles unless we're running in a very small low current mode where we need to map out acceptances and so forth. we measure the scattering by way of just all the flux that comes through for a particular polarization settings. And we're going to flip the polarization at a very high rate, again, to control as many of the systematic uncertainties as we can. It's an 11 GeV beam from the CEBAF accelerator at JLab. Scattered electrons are in the region from about 2 to 8 GeV, relatively low Q squared. 70 microamps is the highest power that we can stand in this target, which is also a Twitter force. It's going to have 4 kilowatts deposited in liquid hydrogen, and it's sort of taking this to a level that it hasn't been before. But the engineering has been reviewed and is quite sound, and we're looking forward to building the thing. Again, more or less for experts, this is our uncertainty budget. I highlight the beam polarization uncertainty of about 0.4%. We've had a CD1 review that was positive. Another review is coming up, in fact, tomorrow. There are a lot of these things very often to make sure that everything's on schedule. We're finalizing the design. Pretty soon, orders are going to be placed for components. Metal's going to start getting cut, building these magnets, building the detectors, and we're on path to install sometime in 2025. We'll begin to take some data, and then we will have 3 years of dedicated running to get the statistical precision that we need for this experiment. Just to give you an idea where we're going with this, this is the plot I showed you before from the particle data groups. Compilation of values of sine squared theta as a function of the scale. This is that discrepancy that I mentioned to you earlier by measurements at the z-pole. This dot with its vertical size is our goal for precision for sine squared theta using the Muller experiment. It's this experiment, SLAC E158, that's the precursor experiment where electron-electron scattering was measured. We're obviously trying to beat that level of precision by an enormous amount. It's not only statistical precision, we have to measure everything with all the systematic uncertainties, and beam polarization, like I said, is the one that I care about a lot, and we're trying to go for 0.4%. We're actually trying to get to that level using 2 different techniques, both Muller scattering, a Muller polarimeter, and also a Compton backscatter polarimeter, so we can cross-check them against each other.
What is the LHC point on that graph?
Okay, it's again a measurement at the z-pole. You see this weird arrow here? This means take this point, move it over here, and the Tevatron point, move it over here. They're measurements of z decays.
Okay, thanks.
Yeah. It's a strange way to plot it, but I guess it just didn't want to put everything on top of each other. I should remember what the specific measurements are. One of the interesting things about the LEP and SLC points is they're different reactions. I think SLC is a measurement of hadronic final states, and LEP is a measurement of leptonic final states. That's where they got the highest precision, and they don't agree. That's it. Parity violating electron scattering. It's something that I've only been doing now myself for the past 5 or 6 years, maybe a little more than that. And it's very cool. It's a really neat tool, and we're getting a lot of. It's a lot of fun. You really meet a lot of interesting people when you're trying to do these precision measurements of really tiny quantities. We're really pleased with the result that we've gotten from PREX and CREX, and as Keith pointed out, people are going to be spending some time now chewing on the results, trying to figure out what it all means. And now we're working on Muller, trying to find new physics by doing precision measurements at low energies. And hang on, it'll take a few years for those results to come out. Our first result will be based on our first engineering run, and that precision should be about the same as the old SLAC E158 result. But then after that, we'll just dive in and take data for a few years and try and see if we can see new physics at very high energies. So thanks a lot, everybody. This was fun. I look forward to coming up and seeing you guys in person at some point.
So thank you very much, Jim. As always, exciting, well presented, and understandable, you know, the whole thing. So thanks very much.
You bet.
And I invite anyone with questions to ask Professor Napolitano.
I've got some hands raised. I thought Steve Gervin's
Okay.
hand raised, but. Or were those claps?
Actually, I was just clapping my,
Oh, sorry.
but I'll comment that I enjoyed your example of the weakly anharmonic oscillator as
Oh, good.
probe high energy physics. Thanks.
Other questions? Come on, couldn't have been that clear. Oh, Carson, is that a hand raised?
Yes, it is.
Ah,
I'm also
wonderful.
clapping. No, yeah, thanks for this really nice talk. That was great. Do you see Muller as the end of the experimental effort in this direction, or what would be the future after Muller? Or are we reaching the point where it's difficult to go down further that road?
Well, you know, when I first started thinking about this stuff when I worked at JLab with Keith, I would have said no one's ever going to reach the precision that you need to for what we're doing with Muller now. It's possible in part because you know, the resources were found to build this really large scale experiment with very high currents. But it's also possible because people have really nose to the grindstone at JLab with CEBAF have learned how to make these extremely exquisitely controlled electron beams, which are not only outstanding, but even the tiny small deviations from perfectness you have to measure very carefully to make all the necessary corrections. You can probably keep putting your nose to the grindstone and do things better, but at some point you just hit some fundamental limits. You know, Muller uses 70 microamps on a 125 centimeter long hydrogen target. How are you going to get a factor of 10 more than that? And a factor of 10 only buys you a factor of 3 in the uncertainty, right? So statistically. So I don't know, Karsten, I was wrong 30 years ago. So maybe if I look 30 years in the future, I would be wrong again if I said you couldn't do better, but I'm not sure that would be. Now the accelerator at Mainz is building an outstanding polarized source. And again, it's a different kind of accelerator. It really excellent controls everything. So it's possible that that precision measurements might be possible at Mainz. You know, everyone's always knocking at the door. My guess is that if Muller sees a convincing signal that doesn't agree with the standard model, people will figure something out.
Yeah.
But yeah, this is definitely pushing the limits of what we think we can do now and what we have available to us. My opinion. Sid has a question.
Yeah, so on the plot showing the running of the coupling constant,
Yeah.
there's at extremely low Q squared, the cesium atomic parity violation result.
Yeah.
All right, so are you guys still interested in what cesium can tell you as the atomic calculations get better and better and better?
I imagine, sure. It's one standard deviation away from the curve. I remember those early days too. In fact, I remember hearing Gene Cummins give a talk about the experiment he was doing in thallium, which turned out to have different problems. And I guess it was Carl Wyman who finally figured out how to do cesium with the precision that he did. I don't know what the limits are to the atomic calculations, but it seems to me that if, and I don't even know how much of that error bar is theory compared to experiment. Maybe you do, but if that error bar can be made smaller by theoretical physics calculations, my gosh, absolutely. I would actually bet that given modern techniques, maybe you could figure out a way to do the cesium experiment or maybe even the thallium experiment to higher precision. My recollection of this business was that people were getting, again, when I was a graduate student, was that people were getting different results for cesium and thallium. They couldn't really figure out what was going on. People were making different models, different standard models with different groups instead of just SU2 cross U1 that could accommodate the different electron quark or electron nucleon couplings. But then the Slack experiment came along and bang, they got the right answer and people stopped talking about atomic parity violation. But God, yeah, I mean, if that experiment can be done better, I mean, you want all of those points to be sitting, you want them all to be perfect, right? And, precision measurement. There are a lot of examples where precision measurements didn't agree with theory. It turned out to be really interesting that they didn't. So that's a long-winded answer, but the short answer is yes.
Okay.
Okay, let's see. Anyone else? I don't see any hands raised.
And it's 5 o'clock. So everybody go back to work for another couple hours before you go home to your families. We know how it all works. And and hello to all my friends. And it would be great to come up and maybe give you guys a technical seminar on some of the stuff sometime in whatever post-COVID land looks like. Meanwhile, everybody stay healthy, stay safe, and we'll catch you later.
All right. Thanks again, Jim, and wonderful talk as always. So take care, and yes, you're welcome to come anytime, all right?
Okay, I promise not to just show up on your doorstep. Take care, everybody. Have a good evening.
Take care.